So I want to sketch a proof of this theorem that given any non-zero finite dimensional vector space, any two bases of this vector space has the same number of elements, and this number n will be then called the dimension of the vector space. So the main work needed, so we'll do it in three lemmas. We have written them down. Let's take them one at a time. The first one requires some calculation actually. It says that if you have a finite basis B of the vector space, and suppose you're given a vector V in capital V, and suppose little b is an element of this basis, such that when you write V as a linear combination of the elements of capital B, then the coefficient of little b is non-zero. Then you can take this basis B, throw away the element little b, and instead add the vector V, and what you get will still be a basis. Let's see why. So, sketch of proof. I'm going to label the elements of B as B1, B2, Bn, where the first one is my little b. Okay, just name them as like that. Then what am I told? That if I write V as something times B1 plus something times B2 plus something times Bn, where the alphas are always in F, then this first one, alpha 1, is non-zero. That's the coefficient of B1, meaning the coefficient of B. That's what is given. So this is the given condition. And what do I need to show? I need to show that if I take this set, B1, B2, Bn, I throw away B1, which is B, and instead add V. This is a basis. This is what I need to show. So I need to show that this set spans and this set is linearly independent. Now look, B1 can be written in terms of these guys. To do that, you just take the equation that is given up there, move the B2, B3, etc. terms on the left, so then you get alpha 1 B1 is V minus alpha 2 B2 minus alpha n Bn. And then you divide by alpha 1 on both sides. Alpha 1 is non-zero, that's the key condition, right? So you have seen now that B1 is in the span of V, B2, Bn, because it's a linear combination of these guys. B1 is there. But B2 is also a combination of these guys, of course, because B2 is in that list already. Same for Bn. That tells you that these guys, B1, B2, Bn, can be written in terms of those guys. So anything that can be written as a combination of these guys can also be written as a combination of those guys. So verify from here that the span of B1, B2, Bn is a subset of the span of V, B2, Bn. But this is exactly V, so this is equal. So these guys do span V. That's all right. Now we have to check that they're linearly independent. How do I see that something is linearly independent? I pretend, so suppose we take some scalars such that beta 1 V plus beta 2 B2 plus beta n Bn, this combination is 0. I want to show that all the coefficients, beta 1, beta 2, beta n, they are all 0. What do? Well, you just substitute the expression for V. This implies beta 1 times alpha 1 B1 plus alpha 2 B2 plus alpha n Bn plus beta 2 B2 plus beta n Bn, 0. So now if you collect terms, you get beta 1 alpha 1 b1 plus, what's the coefficient of b2? You get beta 1 alpha 2 from here plus beta 2, etc. And what's the coefficient of bn? You get beta 1 alpha n from the first series and then beta n from the second one. This combination is 0. But now, I don't want to write much more. You know that b1, b2, bn is a basis. So b1, b2, bn are linearly independent. b1, bn are independent. That tells you that these coefficients have to be all 0. So this is 0, this is 0, this is 0. That's what linear independence means. But then alpha 1 is non-zero, remember? Right here. So if alpha 1 is non-zero, but beta 1 alpha 1 is 0, that implies beta 1 is 0. But now that beta 1 is 0, all these just go away. So that tells you beta 2 is 0, beta 3 is 0, beta n is 0. It's written out more systematically in the notes, but this shows that these are independent. So V, B2, Bn, this set is also independent. And that shows that they form a basis. That's the first lemma. The second lemma says that suppose I have a linearly independent set, V1, V2, Vs, and then some more. So this k is strictly bigger than s. I didn't say that, but there's a bunch of vectors, s of them, and then some more. And then I have a basis b, which has the first s things from there, and then some other stuff, some u's. Then you can cross off one of these u's, delete one of the u's from this list b, and instead add the next one from that list, and you'll still have a basis. That's the statement. So why is this true? Take this vector Vs plus 1 and write it as a combination of elements of B. B is a basis after all, so you can write this guy as a combination of elements of B. So some combination of the U's and then some combination of the V's. The thing that you have to observe is that one of the alphas must be 0. Some alpha j must be non-zero, since otherwise, if all the alphas was 0, then Vs plus 1 would be a linear combination of the previous guys. And that's not possible because these guys are independent, you see. So one of them cannot be written as a combination of the other guys. So which means that when I write Vs plus 1 in terms of all these, one of the u's must occur. Some jth term must occur with non-zero coefficient. But that's exactly the setting of the previous lemma. Tells you that you can delete this jth guy and instead add Vs plus 1 and you'll still have a basis. Now apply previous lemma. Okay. So what does this say? It says that if you have a basis that looks like a bunch of u's and a bunch of v's, and these v's are linearly independent, and there is one more v which is still linearly independent with these v's, then you can add that guy at the cost of removing some u and you'll still have a basis. Okay, let's remember it in this way, and read the next one. Oops. The next one says, let V1, V2, Vk be a linearly independent set, and suppose U1, U2, Um is a basis. Then you can remove, so you have U1, V1, V2, Vk independent, and you have U1, U2, Um a basis for the vector space. Then you can remove k of these things and instead add in these guys, and then what you get would still be a basis. So there is a k element subset B naught of B, such that if you remove those but add the v's, it gives you still a basis. And this one is very straightforward. It's just applying the previous lemma repeatedly. So you have a basis here, and you have a bunch of independent sets here. So you take this one, and when you write that in terms of these guys, some coefficient of u is non-zero, so you can throw away some uj1. Throw it away and add v1 to the list. It's still a basis. Now you look at v2. Write v2 as a combination of these bases. Again, one of the coefficients of the u's have to be non-zero, because otherwise v2 would be dependent on v1. So there will be some uj2 which appears with non-zero coefficient. You throw that away and instead add in v2. And you go k steps like this and you get your lemma. Okay. And once you have this, the theorem is actually immediate. Because now, what does the theorem say? The theorem, you have to prove that you have two bases that they have the same number of elements. Right? So now let's say I have two bases, v1, v2, vk, and u1, u2, um. And without loss, I can assume that m is bigger than or equal to k. One of them will have more stuff. Let's say this one has more stuff. Then this lemma tells you that you can throw away k of these guys, k of these u's, and add v1, v2, vk, and it's still a basis. So b1 and b. Then b minus b naught union b1 is a basis, where b naught has size k. Right? Some b naught in b by the previous lemma. But then here is a set which contains b1. b1 is already a basis. If you add something to a basis, it can no longer be a basis, because whenever you add something more, so I claim that this has to be empty set. Why? Because if it is non-empty, then I have a basis and then I'm adding something to it and it's still a basis. That's just patently impossible. As long as you have a vector here, you can write this guy as a combination of b1, because b1 is a basis. So this shows immediately that b minus b naught is empty set, which means b is b naught, which means the size of b is the size of b naught, with k, which is the size of b1. So b1 and b have the same size. Okay, so after you remove these, there cannot be anything more left, because if there is anything more left, then you get a basis plus some extra stuff. That cannot be a basis anymore. Okay. So that gives you the theorem, and that lets us define the dimension, which will be the key tool for studying these field extensions, the vector spaces that we get.